Okay, so today's Friday, September 18th, and this is ECE641, and we're going to finish up the material on non-causal models, which is important material, but this is the Gaussian case, and so there's a lot of different ideas floating around. Maybe I can also do some problems. I'll do at least one problem, discuss at least one problem. Are there any questions other than, yeah. Okay, so basically the key idea is what? That if in the non-causal, so non-causal, you have that xs minus g of xs, right? Or x, I'll say it here. And then if the prediction variances are all the same, this is just sigma non-causal squared, okay? I guess, let me write it like this. So this is xs minus, this is gs convolved with xs, okay? Like that. And by the way, this could be like regular convolution or it could be circular convolution. And then this is epsilon s, okay? And so basically, so this is equal to 1 over non-causal delta of n minus, or g, delta of s minus g of s convolved with xs. Okay, and what ends up happening is that the precision matrix B is equal to what I call I want to make sure my notation is consistent. Oh, shoot. By the way, you read the notes, right? Yeah, gamma. I minus g, like this. So, so this is the precision matrix. Which, by the way, it's usually the precision matrix that you're dealing with. Okay. So intuitively, for the say circling case, what ends up happening is that you get B looks like this. It's a symmetric matrix. It has to be symmetric because it's the inverse covariance matrix. And then it's like times 1 over sigma non-causal squared times this matrix is 1s along the diagonal. And then over here it's minus gi minus j minus gi minus j. So the off-diagonal elements are the prediction coefficients, the non-causal prediction coefficients. The diagonal element is 1, and then this is the normalizing constant. This is the case, which is the kind of common case, where the prediction, where it's homogeneous, where it's stationary. Now, the problem is that you have some kind of boundary issues associated with if you have a finite length sequence. But you can fix that if you want by using a circulant boundary, okay? Then you do circular convolution and everything's good because there's no end, right? If you take the signal and you wrap it around, there's no end boundary to cause problems, okay? So, fine. So the point is that if you look at this matrix, the off-diagonal elements are the prediction coefficients. So a typical structure for this matrix, by the way, would look like this. I mean, this is where, in 1D, it might look like this. So you'd have points 1D, okay? You'd have points, they should really fix this light. You'd have points like this, right? This would be like xn. And then what would happen is that epsilon n, or the B matrix, so the B matrix would look like this. 1 over sigma non-causal squared. And then it would be like 1s along here. And then these would be like minus 1/2 this would be 0. This is minus 1/2. This is minus 1/2. These are zeros, okay? So it's like for every pixel, if you want to predict this value, you take the average of its two neighbors. These are the 1/2 of the prediction coefficients, the non-causal prediction coefficients, right? That would be like sort of reasonable, okay? So that's the intuition. That's how you remember it. So usually the off-diagonal elements are negative because for most signals, for a typical case, the signal is low pass. And then if you want to predict this point, you average its neighbors. I mean, you could have a high pass situation where you have like the average and you multiply by -1 because the signal's oscillating. But in a conventional low frequency variation case, you would sort of take the average of the neighbors, right? So this gives you some intuition. So the fact that these are 0 out here means that these things are not neighbors, okay? If they're not neighbors, it means that this point is conditionally independent of that point given the neighboring points, right? So that's kind of the intuition. You have neighborhood interactions. The reason you do this is because it's a simpler model, but it results in global interactions. Because these pixels that are far apart, they're conditionally independent, but they're not independent. They're highly correlated, okay? So you get long distance interactions with a low order model. That's the value of all this, right? It's a simple way of enforcing long distance interactions. So then what happens is that there's some interesting things. You read the notes, right? You read the notes. So let me just go to the notes and I want to because there's this equation we talked about last time. Okay, so this is the equation, right? The idea is that, okay, so what does this equation mean? This relates the non-causal and the causal models. So you can, H here is the causal predictor. It's the minimum mean square error causal predictor. Think about it in 1D, because in 1D and 2D it's pretty similar, really, okay? So this could be a 1D or a 2D non-causal predictor. Then G is the 1 or 2D non-causal predictor. So when you apply this filter, you get the prediction error, because it's the difference between a delta and the prediction, right? This is the causal prediction error, okay? If you take these two filters, if you convolve this with its time reverse, okay? If you convolve something, okay, if there are electrical engineers in the room, if you do convolution, the thing with convolution that everybody always talks about, like there's like certain things people talk about, you know, as undergraduates in electrical engineering, it's like the thing, okay, is the so-called flip and shift, okay? I'm sorry, the flip and shift, right, yeah. For some reason, every time I say flip and shift, I always think about steak and bake. Steak and shake. Yeah, steak and shake. There used to also be a thing called shake and bake. I don't know if they still have that anymore. When I was a kid, it sort of existed in the same part of the universe as Hamburger Helper, you know? And, you know, so in flip and shift, you have the two signals, and you take one and you flip it, and then you shift, okay? And then you take the inner product, and then the output, that's the output. And that's how you do convolution, right? Flip and shift, right? So if you flip the signal before you do flip and shift, right? You do flip, and then you do flip. Well, if you do flip twice, it comes back the way it was, right? So then if you do flip and shift, it's just shift, okay? So you're just doing shift. So if you're just doing shift, you're getting a correlation. So this is just a way of representing the correlation between two things, okay? So what this is saying is that if I compute the correlation between this filter, okay, and like a typical case would be like this. I mean, I think it's helpful to think about the simple typical cases, because then the more complicated cases fall out of that. But it's usually the simple thing that everybody gets confused about, okay? So in the simple case, you just have like h of n is equal to delta n minus, say, some value, I don't know. Oh, we'll say rho, okay, of delta n minus 1. That means that you have these inputs, right? And this is like xn, this is xn minus 1, this is xn minus 2, right? This is yn. So this is going to, you multiply this by 1, you subtract, you multiply by rho and you subtract it, right? So you're taking the prediction is rho times the previous one. And a typical case would be like rho equals 0.9. So your prediction of the next value is 90% of the previous value, okay? That's pretty simple, right? So the impulse response looks like this. It looks like this is 1 and this is rho. Okay? That's what it is, okay? Now what happens if you take that function and you correlate it with itself? What's the output if you just do an autocorrelation of that function with itself? So this would be delta n minus, this is delta n minus h of n. That's what this function is here, right? Now, if I take the convolution of delta n minus h of n with delta n minus h of minus n, that's the correlation. What's that going to look like? Okay, what's it at 0?
1 plus rho squared.
Yes, 1 plus rho squared. So at 0, it's 1 plus rho squared, okay? What's it at 1? Rho. And what's it at minus 1?
Rho.
And what's it at 2? 0. Okay? So that's kind of interesting, because this is a symmetric function now, right? This is sort of the non-causal predictor, but it's not the non-causal predictor because of the fact that, see, I use the word sort of. Whenever I stick sort of in, anything could be true. But this is sort of the non-causal predictor. It's not the non-causal predictor because at time 0, it's 1 plus rho, and it has to be 1 at rho minus just time 0, right? Because, well, actually, it did me a favor by turning off, because actually the contrast isn't good when otherwise. I wish I could move that crazy thing out of the way. What it's saying is, so this is the convolution with this, right? And it's supposed to be equal to this. What is this? This is the non-causal prediction filter, which is like the delta function just is the value you're trying to predict, and then minus the predicted value, right? So this is the prediction error when you apply this filter, right? G has to be a symmetric function, because otherwise the power spectrum wouldn't be real, okay? So that's good, because this correlation of this thing with itself has to be symmetric, right? But the only problem is that the value at time 0 is not the same for both sides of the equation. Because over here, the value at time 0 isn't 1. But over here, the value at time 0 is 1. So these constants here account for that scaling factor, okay? You see what I'm saying? So the point is that if I know h if I know the models of the causal case, I know H and I know this is sigma C, I can calculate the non-causal model parameters. In fact, I just did that here. I gave you H, and from that we calculated this. It's not quite the non-causal prediction filter yet. Okay, I'm going to do that in just a minute. But from this, I can calculate the non-causal prediction filter. Okay, let me just do it. Blank. Okay. So the point is that there's a relationship between the causal and the non-causal case. Okay. So if causal. So we'll say sigma causal squared equals, I don't know. Well, we'll just say it's sigma causal squared, okay? And we'll say that Hn is equal to delta rho times delta n minus 1, right? So that's the predictor. So in that case, then non-causal, so we want to compute the parameters, right? So in this case, we know that, that equation, hold on. I don't want to put the thing up again because it'll take, okay. We have that, okay. So if I correlate this thing with itself, we have that sigma, okay. We have that delta n minus gn is equal to sigma squared non-causal over sigma causal squared times delta of n minus h of n convolved with delta of n minus h of minus n, okay? That's this thing over here, so I'll just plot it again. This thing is 1 plus rho squared, and then this thing is rho, and this thing is rho, okay? Right? Did I do that wrong? I think I did it right, yeah? Did I do that right? Okay, any questions? Because I thought I heard a question. Did I do something wrong? Yeah. It should be negative rho. Oh, thanks. Thank you very much. That would have made no sense. You can actually do it that way, but it's super counterintuitive because it corresponds to a high frequency signal instead of a low frequency signal. Right, I forgot to put the minus sign here. So that's correct. Thank you very much. You saved me. Minus rho. This is minus rho, okay? Correct? Okay, so let me draw that again. Sorry about that. It's minus rho. It would have made no sense when I was done, too. I should have caught that, okay? You're totally correct. Okay, so now what happens is this is like the non-causal prediction filter, right? So what happens is that from here I can figure out what G is. What does G have to be? Gn is equal to, what is it going to be? It's going to be delta of n minus 1 plus delta of n plus 1 times rho, okay, over 1 plus rho squared. Okay, now you might be saying, what the heck? How did he know that? Okay, it's super intuitive once you understand it because, okay, this value, this has got to be 1 because this is equal to this. So this is 1 at 0 minus g. So the negative of these is g, okay? But I have to scale this first so that it's 1. So I'd have to divide everything by 1 plus rho, okay? So from here, I kind of go to something that looks like this. 1, and then this becomes minus rho over 1 plus rho squared. And this is minus rho over 1 plus rho squared, okay? See? And then these two impulses become G, the prediction filter. So what's the upshot? The upshot is that if you have a signal in 2D, okay, in 1D, and let's say that your optimal predictor here is to multiply by rho, and then minus, plus, and then subtract, and this is epsilon n. That's the causal prediction, right? You might think, if you didn't think about it too carefully, you might think, okay, so this thing is xn minus rho times xn minus 1. You might think that, okay, now what if I'm predicting in 2D? The first thing you might think is you might say, oh, this is the optimal predictor. It uses all the previous information. So if I'm going to predict this value given the past, I just subtract that, okay? So therefore, there's no additional information for the future. Well, that's not true, okay? You might initially just say, oh, well, I have all the information, so this is the optimal predictor. Someone told me this is the optimal predictor, so it's the optimal predictor, I'm done. No, well, obviously that's not true. If I have future information, I can predict it better. It's like, if I want to predict tomorrow's stock price, you know, if you make this a real problem, particularly one where you lose money, it tends to become clearer, okay? Okay, so if I'm going to predict tomorrow's stock price, I might say, oh, I'll use today's price as my predictor of tomorrow's price, right? But if I had the future knowledge of the future price, obviously I could do better, okay? All right? I mean, if you tell me what the price is going to be, if I know today's price, I don't know tomorrow's price, but I know the day after's price, what are you going to do? You'll be like, oh, I'll take the average, okay? Right? Okay? A lot of learning, what you have to learn in classes like this is forgetting all the things that you learned to not understand, okay? Okay, and just think about it kind of clearly. Okay, so if you're going to do the non-causal prediction, clearly you can do better, right? Now, what you might do, okay, so the naivest thing would be to say, oh, I can't do any better. Well, that's wrong, okay? That's obviously wrong. Of course I can do better, okay? Then the next most obvious thing to do is what? In my opinion. Okay, I'm a flawed human being, okay, but this is what I would do, okay, if I wasn't thinking real hard. If I had the future information and the past information, what's the next, in my opinion? Obviously, it's a subjective call because it's wrong, okay? But what, if I was going to do the next most complicated thing that turns out to be wrong, what would it be? You take the average of the two predictors, right? So you might think that what you would do is you'd say, oh, I'll take this one and this one, I'll add them together, and I'll subtract it. Minus, plus, and this would be epsilon. You might multiply by rho and rho, because you'd say, well, okay, I'll take the forward predictor, I'll take the backward predictor, I'll take the average. Seems reasonable, right? It's better than a really dumb thing of not doing anything all, right? It turns out it's not the optimal thing. What's the optimal thing? That's what we just calculated here. You do what? This multiplies by what? It's rho over 1 plus rho squared. I guess if rho's 1, then this is the average, right? Because if rho is 1, if I predicted the entire stock price by just taking today's, I just multiply by 1, then what I would do is I'd say, okay, then that would be 1 over 1 plus 1. So what's 1 over 1 plus 1? 1/2, okay? So if I take 1/2 today's stock price and 1/2 the future, not tomorrow, but the day after stock price, then I'll get the average, right? Okay, but if rho isn't 1, then it's different. So if rho is like 1/2, then it would be 1/2 over 3 halves, right? Is that right? Okay, yeah, let me just do it because over 1 plus 1/2. So that's equal to
1/2 squared.
Oh, 1/2 squared. Okay, yeah, that's even better. So that's 4. It'll be 2 over 4 plus 1. Is that correct? So it'll be 2/5, which is, you know, more than 1/4. Okay, which would be half of a half. Okay. So you see what I'm saying? Now, so what this also tells you is any reasonable person would understand and wouldn't need to have this course to learn is that if you told me today's stock price and you told me the stock price the day after tomorrow, okay, I should be able to do a better job of predicting tomorrow's stock than if I just had today's stock price. That was a long sentence, but hopefully that made sense, right? Yeah, okay, because I have stock price, this is time n minus 1, and this is the stock price at n plus 1, right? And I'm trying to predict this stock price, right? If I just have this information, I can't do as good a job, you would think, than if I had both, right? Certainly, you could just throw this out, so then it should be better, right? Well, that is the non-causal versus the causal prediction variance. So I can compute this ratio, okay, by looking at the solution to this equation at time 0, for n equals 0. For n equals 0, at n equals 0, what's the left-hand side of this equation equal to? It says 1, right? Then this thing is sigma non-causal squared over sigma causal squared, okay? And then what's this thing equal to at time 0? Yes, but in general, what's it equal to for any h? For any function. You're correct. Your answer was totally correct. I just want a more general answer for the more general case. In the more general case, if you take the correlation of these two functions, right? Okay, the idea is that my left and right hand are supposed to look exactly the same over here. Okay, they don't. One's left. You know what I'm saying, right? So if I was a perfectly symmetric human, right, then and you did a shadow projection, then it would be exactly match, right? So in this case, the correlation at 0 at time 0 is what? It's what?
The energy of the signal.
Could you say that a little more slowly?
Energy of the signal. Sum of square.
It's the sum of the squares, right? Now, one point, this is the delta function. I'll make my thumb the delta function, okay? This is really bad. You guys are very patient with me, really. Okay, so this is the delta function right here, right? And then these are the h's, okay? So the delta function, I get 1 squared. So 1 squared is 1, right? Plus the sum of the squares of the h's, right? So this thing is 1 plus the sum from n equals 1 to infinity of hn squared. Okay, so from that, I get that sigma squared non-causal is equal to sigma causal squared over 1 plus the sum from n equals 1 to infinity of hn squared. This is always positive because the h squares are always positive. So 1 is 1, and then if you add some positive stuff to it, it's got to be more than 1. So that means the non-causal prediction variance is always got to be less than the causal prediction variance. And they're equal only in the special case when the h's are zeros. But the h's are zeros only in the case when the minimum mean square error predictor of the future, causal predictor, is 0. That only happens when the samples are independent. If there's any correlation between the samples, then you can always do some prediction. But if they're independent, then there's nothing to predict. So if they're independent, then the prediction variance is going to be just whatever the variance is of the sequence. and the non-causal prediction variance will be the same. So does that make sense? So this relates the causal and the non-causal predictors, which I think maybe is a useful idea because it helps you think about the problem, okay? Yeah, the other, then, let's see. That wasn't, the projector wasn't on, right? I think it comes on when I wake up the computer, which is not a bad thing, but I just want to make sure it's not. Oh God, okay, here we go. So this diagram's kind of interesting, in my opinion. So this is sort of a taxonomy of models, okay? So, so you have the set of all Gaussian random processes, right? And then you have like 1D AR and Gaussian model random processes. You know, maybe you could sort of argue that 1D, well, yeah, I think I'm going to go with this. It's fine. They're kind of disjoint, okay? Right? Maybe you could sort of argue 2Ds were a subset of 1D, but I guess it's too late now. I'm not going to redraw this figure. So in any case, that would be kind of confusing. Yeah, okay, anyway, I'm not even going to think about it. Let's make my head hurt. Okay, so then you have the 2D Markov random fields, okay? Now, you can have an order P AR model, okay? So order P AR model. Okay, so let's do the top case first. Let's say you have an order P AR model, okay? So that means you use so let's say P is 2. That means you use the last 2 samples to predict the current sample, and that gives you the mean square error predictors. So all the other samples of the past are conditionally independent given the last 2 samples, okay? Now, if you calculate if you use this technique I showed you to calculate the order correlation, to calculate the non-causal predictor, what's going to happen? You get you get like a delta function here, right? And then you get some things like this, and then they're all 0. So there's 2 of them, right? Now, so this signal is of length 3, right? Now you're going to do a correlation of the length 3 signal with itself. If you correlate a length 3 signal with itself, how long of a signal do you get? Here's the answer, because it's a little tricky. You know, if you take an M length sequence and an N length sequence and you correlate them, how long is, or do convolution equivalently, how long is the result? The result is M plus N minus 1, okay? And if you think about it, because if they're both length 1 and you correlate them, you get something of length 1 out. So you might think it would be M plus N, but it's not. It's M plus N minus 1, okay? So this is 3. So if you correlate it with itself, so it's length P. So if you correlate it with itself, what you're going to get out is something of length what? You're going to get 2P minus 1, right? 5, okay? So you get 2P minus 1, correct? Now, that's the non-causal prediction filter. So, wait, I screwed this up. Oh, no, I screwed it up. It's P plus 1 times 2 minus 1. Because this thing, if it's 2, that's 3, okay? Okay. Do you see what I did wrong? Because the original filter is of length P plus 1. Because if this is an order 2 predictor, this filter with the impulse response is is of length 3, right? Is everybody okay with that? I just confused you. So this thing is going to be equal to 2P minus 2 minus 1 plus 1, okay? Now, if I subtract 1, because of the non-causal predictor has a single, also has the center value, which you have to get rid of because you're not going to use that, then it becomes 2P. And if you divide it by 2 because of the symmetry, it comes out to P. So the point is that a order P AR model leads to an order P order P causal model leads to an order P non-causal model in 1D. Okay? Now, the other way turns out to be true also, which I'm not going to attempt to prove, but it used to be in like the signal processing classes, we would teach this thing called minimum phase, the Wiener filter spectral factorization. It's this trick you use, okay, to compute, and it's some tricks, okay? Basically, it comes down to the fact that because you can factor polynomials, you can find, you can factor this thing, and you can solve that equation in the other direction. See, what I did was, okay, for this equation, I gave you h, and then we calculated g, right? But what's not so obvious is in 1D you can go the other way. You can give me g. Now obviously there's some g's that aren't going to work, but there's some g's that are just invalid. It has to be a valid g. Okay, well what do I mean by valid? It has to correspond to, well, it's got to be symmetric, and it's going to turn out that its Fourier transform, that this function has to be positive definite, which means that its Fourier transform has to be positive, okay? So there's some constraints. So as long as you pick a valid g, it turns out I can find an h, which will solve the problem. Now, it's not obvious. The fact that you can find an h actually isn't so surprising because you could just take the Fourier transform and take its square root, okay? But what makes it surprising is that h has to be causal and finite order, okay? So it's not obvious you can do that. It's not super complicated, but it's not super obvious either, okay? You have to do this thing called spectral factorization. So in any case, you can find it, okay, miraculously. So it turns out that you can go this way or you can go that way, okay? So they're equivalent. That's why it shows that the two things are the same, okay? The two things are the same. In 2D, that's not true. And here's the intuition behind it, which is kind of interesting. If I took, okay, in 1D it shows if I take that function and correlate it with itself, I get something with a support like that, okay? That's what we just did. In 2D, it's kind of interesting. If I take this thing here, okay, and this is the non-causal predictor. If I take the autocorrelation of this function with itself, I get something that's shaped like that, okay? Something here is clearly weird, okay? Because what ends up happening is that if you count the number, there's a parameter associated with each of these dots, okay? So it turns out that, now this function has to be symmetric, whereas this function does not. But if you take the number of dots here and divide by 2, it's not equal to the number of dots there. So the number of parameters in this model is not the same as the number of parameters in this model. So right off the bat, that tells you something's deeply wrong, okay? Because the two models can't be equivalent. Intuitively, it doesn't seem like the two models can be equivalent if they have different numbers of parameters. Okay, and actually if I count it here, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5. What's 5 times 9? 45, right? Divided by minus 4, that's 41. Minus 1 for the center point is 40. Divided by 2 is 20. So the number of free parameters in this model is 20, but over here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, good, it worked out. So it's 20 there, and it's only 12 here, okay? So something's wrong, okay? Whereas over here, the number of model parameters is 2, and the number of model parameters is 2, okay? Here you say, well, there's 4 dots. Yeah, but I divide by 2, right? Because of the symmetry, okay? So that's kind of interesting, at least for me, okay? I don't know. Well, it's nice to learn these things once in your life. What can I tell you? Okay, so the 2D model, in 2D, the non-causal and causal model are not equivalent. Okay, and the order P model, forward predictor, is included within the order 2P non-causal, but it's not equivalent to the order P. Right? So upshot is this. Mostly people use non-causal models in 2D, okay, because it's just more natural. And then, and then there's a bunch of other stuff here, and you're going to read it. Here's the general case. So you can do this stuff on graphs. In fact, there's a whole field of research called graphical models, okay? This is just a special case. It's not even a special case. This is just, I could just have renamed this section graphical models, okay? It's the same stuff. And yeah, what can I say? I mean, there's other topics, obviously. It's a big field. There's a lot of things you could do. But this is graphical models. So these can be on graphs. They don't have to be on 2D lattices. They don't have to be image pixels. They don't have to be time sequences. And there's also was, at one point, a lot of work on using these on trees. You know, you can do, well, we'll talk about hidden monocle models later. So you could do random processes on trees. Trees are kind of an interesting special case because they're not 1D, but they're sort of 1D because they have no loops in them. The problem with 2D, the reason you run into all these weird problems is that they have loops in them, okay? And in 2D, the graph structure has loops, okay? So that there are loopy dependencies. Okay, now I want to answer this question that came up because I think it was a good question. Charles sent me an email. The studio audience, okay? I got a question from the studio audience. Actually, if you have questions and you email them to me, that's good because I can answer them in class because it gives me a little time to look at the question and make sure I'm clear. Sometimes if you ask me right in front of class and I haven't had time to think about it, I can get a little disoriented as I'm looking at the notation. So, here this is sort of a general case of a Markov random field on a lattice. And the idea is that these are the neighbors, and we're assuming that each pixel is only dependent upon some number of neighbors, and that the number of neighbors is constant, okay? Because otherwise the notation gets really messy. And that there's sort of a stationarity or homogeneity constraint, which is that the predictor is invariant to the pixel, the prediction coefficients, okay? So this is like a linear predictor, but it could be applied on a general graph. It doesn't have to be like an image or a 1D case. And the prediction variance is also constant, okay? And it's saying, okay, now it's asking some questions. It says, can you compute the ML estimate of H and sigma? Okay, maybe I should have made HG to be more in keeping with the notation of the section, but I guess I could change that. But so when we in the causal case, we could predict the maximum likelihood estimate. There was a homework problem where you computed the maximum likelihood estimate, okay? Why is that? Oh, because it's a result of two things, okay? One is that you have the probability distribution. You had, for causal, you had something like exponential of -1 over something like this, sigma causal squared of, you had y minus ax squared like this, where this thing was upper triangular, right? Lower triangular. You used, yes, right? So, and then this thing had some variance junk in it, but the most important thing was that there involved something, and I think it was the determinant of A. But this is equal to 1, so it's constant, okay? And then there was some other stuff here, okay? So when we tend to do maximum likelihood estimate, the ML estimate was x hat, or h hat, equals arg min over h of y minus ax. And a was really a function of h, okay? So we just, so this was equal to the arg min over h of the sum over n equals 1 to whatever n of yn minus the sum from k equals, say, 1 to p of hk. Wow, you guys actually know what I'm talking about here. Oh, this is x. I'm sorry, shoot. Sorry about that. That should be an x. I was mixing my metaphors because I was working on a different problem earlier today. N minus k squared. So in other words, it's just a prediction error, the causal prediction error. But you can solve the minimum mean square error causal prediction error. It's the least squares fitting problem, okay? It's very standard, okay? Now, the problem when you go to the non-causal case, is that what ends up happening is this. What ends up happening is that you have the probability distribution, and there's some kind of thing over here, it's exponential of minus 1 over 2 sigma non-causal squared, and then this is, it turns out you get something like this. You get, in the notes, it's, you get x transpose. Well, first of all, this is bx, okay, like this. And b here is I minus g, right? That's the prediction filter. So then this thing here is, here's the problem. The determinant of b is not 1. Because it's not lower triangular. So what ends up happening is that you have an expression here, and I forget whether you divide or multiply by b. Let me see, as b gets big, that gets small. So I think you have to multiply by b to the 1/2, okay? Right? So what ends up happening is that you have this term which depends on g, the prediction filter, which is the determinant of b. And the determinant of b, well, that's complicated because b is a big matrix, potentially. So calculating the determinant of b is complicated. Now, there was a problem in the previous chapter where there's an asymptotic limit for the determinant of b that you can compute using something called the Paley-Wiener condition kind of a thing, okay? So asymptotically, if B is a circulant matrix, or if it's Toeplitz and it goes to infinity, then you can use a Fourier transform and compute the frequency response of this thing. And then basically, the determinant has the interpretation as the product of the Fourier transform coefficients, okay? Did you guys look at that problem? Because up here, just saying that, it's got to sound really confusing, okay? But if you work through it, it's actually fairly intuitive. But the most important thing is this, okay? That screws everything up. That's why people like causal predictors, because everything works out. If you do the non-causal case, it doesn't. And the intuition is because you have a loopy dependency, okay? That loopiness causes problems. The non-causality causes problems, okay? So that's the answer to that question. But the other answer to the question, so the next part B of the question is this. So one might think, and early on in this field, people used to do crazy stuff like this. They'd say, well, you'd say, okay, the probability distribution of x, they'd say, is equal to the product from n equals 1 to, say, n, of the conditional probability of xn given xk for k not equal to n. So in other words, what they do is they'd say, oh, I'll look at the conditional probability of a pixel given all the other pixels, and I'll take the product of all those conditional probabilities. And that's sort of like the probability distribution. No, it's not, right? I mean, that's wrong. This is wrong, right? You can't do that. You can do it when it's causal. You can take the product of the conditional probabilities and it's equal to the probability of the sequence when it's causal. But if it's non-causal, it doesn't work. There has to be some ordering of the pixels. Are people following what I'm saying here? Okay. So, but nonetheless, they sometimes use that because it's more tractable. So you can use, okay, so you can use a thing called the pseudo likelihood sometimes. And you just take the log of this. So you take the sum from n equals 1 to n of the log of p of xn given xk for k not equal to n. And even though it's wrong, you can use it as the basis of an estimator. And it can be useful. So in that case, you'd be like, you'd pick the non-causal prediction error to just minimize the least squares error in the prediction of each pixel given its neighbors, even though that's no longer has the interpretation of being the max likelihood estimate, because you're not accounting for the b. Okay, maybe this is a little bit complicated and subtle. Did you understand that, Charles? At least, yeah. Okay. And was there another part to that answer, or did I answer? C is, oh yes. Oh, right, and then it just says it. So that's like a technique that's used. It was in the homework problems because I figured it's not worth spending a huge amount of time on, but it's interesting and useful sometimes. Okay? And then the next time we'll go, I know it's been getting a little abstract, so the next time we'll start talking about actually solving problems, optimization problems in this framework, okay? Where this is really going is what people call regularized inversion, okay? So in other words, all these prior models are just going to be ways of regularizing the inversion when you're trying to find an image. So this, minimizing things like the norm of x with some b norms. This has the interpretation of being a way of imposing a smoothness constraint when you're doing a reconstruction or estimating something, an image. Right? And that's what we're going to be doing next, okay? So we'll be talking about regularized inversion, map estimation in the context of solving this optimization problem, okay? An optimization problem based on this, okay? All right, good. Thank you very much. If you have any questions, I'll be happy to answer them afterwards, okay? All right, bye.